You know what I forgot before sitting down is I forgot to go get my other device, and now I have oh my gosh, I have Suji Mama. Suji Mama. Oh, I'm sorry, there is something on your ear. She won't let me touch her ear. Suji Mama is making biscuits on my lap, and I am settling down for the Physics Late Live, and I wanted to share it with our friends of the channel so that people can join. But now kitty cats are busy making biscuits and I don't know how to get up. It's a very rainy, cold night, so we're under the blankets already. And we're ready to get settled and start the live. But oh gosh, I have forgotten to get my iPad and or my laptop, and indeed I'll have to now get up. Sorry Baji, sorry Suji, I'm so very sorry. Baji, I'm so very sorry. But Mama has to get up to get my other device in order to share the live. Can somebody share the live? I really don't want to get up. And welcome to this live. This is the late live, Eastern Standard Time from Boston. Please come in, Europe, Asia, Africa, South America, Australia, Antarctica. Welcome to this amazing opportunity to learn physics, and we're about to get started here. But as you can see, I have a certain challenge of mobility, and I can't get up easily because of a certain someone. But anyways, we will start soon here. If you're just joining, thank you for joining. Welcome. And I'll give it a second. Baji has decided to. Hi! Hello everybody! Hi. Hi. Hello everyone! Hi! Hi Red Waist. Alexis. All a little sick. No, just a... I hope not. I hope I'm not too sick. I did just have a cold water, so I think my throat is adjusting. Hi, very cute. Hello. Hi, Vansh Yadav 720. Hello. The Kid Clips says hi. Hi. Hi, Red Waist. Hi, Alexis. Hi, very cute. Hi, Vansh. Hi, Kid Clips. Hello to everybody. Welcome to our Physics Live, late night live, where we study together, uncover some really interesting topics. Hello from Georgia. Ooh. Alexis says, ooh, we're in Boston. Welcome, Georgia. Kid Clips, like the cat. Yes, thank you. Hi, Rahar Janing, hi. Hi, Anna. Hello from California. Hi, California. Hi, Anna. Hi, Michael. Hello from Germany. Very nice. Boston. Always wanted to visit. Love the accents from there. Ooh, yes, we have a lot of immigration in Boston. Is this the guy that sits on the traffic cones? I don't know. Hi, Nolan Styles. Hi, Beta Jews. Hello from Loma Maria. Wow. From Texas. I hope you're doing well. Are you happy and safe out there? Yes, thank you for asking. I do like Boston a lot, and it's been raining all day, but hi, Clicker. Hi. Hi, Nolan Styles, Beta Juice, Kid Clips, Anna Vital, Clicker, Lemony. Hi. Lemony Cat Stuff says hi. Hi. Aku dari Indonesia. Ooh, are you from Indonesia? Perfect. How old are you? Okay. Hi, Christian. Clicker says I'm a sub. Thank you. Raymond says hey. Hi. Hello. So during these late lives, we have been. Will you play music? Probably not. Aku sudah like dan subscribe. Thank you. Are you looking forward to Thanksgiving with friends or family? Sort of. I'm actually not gonna travel for this Thanksgiving. So Gladys Lewis says hi. And then read mine. Hi Gladys. Liked Best Live. Thank you. Thank you, Clicker. Thank you, Anna. Thank you, Lemony. So this year I'm not gonna actually travel for Thanksgiving, so you might see me on the live. I might go live and spend it with you guys. I was gonna spend time with my friends here in the Boston area, but they actually recently told me that they might be traveling themselves to Florida. So you might just see some people coming to Florida from up here in Boston. So they kind of ditched me. We'll see what new plans I make for myself. Clicker says, bro. Hi, bro. So during this very late hour on the Eastern Standard Time zone, that is the East Coast time zone, we have been doing this physics live. Hi, Clicker. This is the best live in the entire world. Thank you so much. So we have been doing this physics live. So I think so this channel, by the way, it's the the kitty cats, me, and my voiceover. I used to actually not appear in the videos too much. Thank you, Gladys. Have a good day tomorrow, says Gladys. Thank you. I used to not really appear in the videos too much. It was just the kitty cats and my voiceover. But then I also introduced some like physics topics, and we've been doing more sort of like books and book reading and discussion. I also have some murder mysteries that we actually read and discussed on the channel. So this is a cute cat lover slash booktuber kind of channel. Clicker says kitty cat, kitty cat. Yes, there's a few kitty cats here. Baji, do you want to adjust here like this? So your cat is cute. Will you play a game? Maybe, yeah. Do you have a game in mind? So OMG, that looks like my cat. Yes, Baji has a ton of tiger stripes. I'm trying to make sure I read all the comments. Might have to pull this a bit closer. Marcus Bezilia says, heart emoji. Thank you for the heart emoji. Hi, Ulvira. Thank you for the emojis. Not sure exactly what you're saying, but thank you. Clicker says, bro, my cat and your cat are twins. Gladys says, I have to go. Bye. Bye. Thank you for joining. Baji heard something and woke up from a not so deep nap. It's okay, Gladys says. Clicker. Robert Lee. Wanted to say hi, and I think you're very pretty. Thank you. Clicker says Gladys. Yes. Awesome. Thank you so much, everybody, for joining at this late time. Sounds like a lot of you are from the East Coast, so it's late for you. Thank you so much for still being here. We also sometimes get people from UK, Finland, Japan, South Korea at this time. So I'm kind of waiting to see if the people, our friends from South Korea, Japan, and some of these other places also join. And then we get started with our discussion and topic of the night. I just rescued a cat like yours. He looks happy with you. You have an interesting channel. Thank you, Anna. Good night. Good night. Yeah, so we do a lot of very intriguing discussions. Sometimes we kind of warm up with the kitty cats and doing not too serious of a chat like here, what we're doing right now, just getting familiar. And then we dive into something much more, I don't know, deeper usually. About what? So we have been covering topics of physics actually, because that's my background. And we have been referencing this book called Einstein's Cosmos. We're actually on the last chapter of this book. And we have been talking about some of Einstein's predictions related to general relativity being confirmed by experiment, even as recent as in the last 10 years or so. So that's what we've been talking about. And I also have a book called Introduction to Astrophysics given to me by the author. That is a book, yes. I'm from the south and it's gonna snow in December. Oh wow, clicker. Goodness, yes. It's raining here today, tomorrow. And Suji is that's the Thunder Fuji. Suji is currently on this other book that I was going to mention. It is a book called Introduction to Astrophysics, written by Barbara Ryden and Bradley Peterson. They're professors at the Ohio State University. Thank you. I'm not going to leave the live till it ends. Thank you so much. These lives actually go pretty long because once we kind of get into the discussion, it's very interesting, intriguing, and can lead to a lot of good chatter. So why I have the Introduction to Astrophysics book is also because I'm going to use it to talk about stellar remnants. So yeah, this live will entail a lot of different things. At least this live answers me. At least this live answers me. Answers you? Meaning like talk to you? Yeah, of course. good. Awesome. Yeah, I'm pretty good at reading all the comments. Sometimes I miss something. If does anyone else want to say hi before I get into the topic and start talking about what we've been talking about on the channel? If any last if anyone want if anyone else wants to say hello and give us a thought before I jump in, um, go ahead. I don't want you to feel shy, but if you don't want to, that's fine too. So I said this would be the late physics get together live. That's because during the day too I went live, and during the day this is really late, so a lot of kids are already asleep. So this is a more grown-up people come to the live, and they seem to be more interested in some of the physics topics that I cover. A lot of the kids really like the kitty cats, and I also like to hang out with them and chat and catch up with them during the day. So I kind of already did that. If you're seeing this, if you're one of my friends who are younger and you're seeing this later on as a live upload, then leave me a comment so that I know it uploaded properly. That would be much appreciated. And if you're new to the channel, welcome, welcome. Thank you so much for joining. Hi, Ismail. Hi, Clicker. And really appreciate you being here. And we will get started with our physics topic. So what I've been doing for several live streams now, so I've been going live. It started with Physics Fridays, where I would pretty much cover physics topics only on the Friday nights. But then, hi, Ismail. I think your message went away, but hello. I was covering the physics topics only on Fridays, but now it's people seem to really like it, so I cover it more often. So I did this last night. Tonight I'm gonna do it, and then tomorrow night, as well as Saturday and Sunday. Sunday might be an earlier live, and then I took off Monday and Tuesday. I might need to spend some time working on some materials as well, because actually soon I want to give a talk, like a presentation on this live stream, and cover some of the topics that I personally worked on. Bye, I have to go to sleep. Okay, Clicker. Bye. Good night. I tried to figure out that live stream presentation mode for tonight's live, because I kind of have a material put together already for some of the topics that I personally worked on that I wanted to share with you, because some people on this channel wanted to see that, but I could not get the streaming to work out at the speed and everything that would have made sense. So we will instead finish covering Einstein's Cosmos, the last chapter, and kind of finish discussing this. And I will draw from my own experiences and background as well, to kind of give you a sort of a covering, a way to cover what's in here. So before I kind of finish up this chapter, which is also because we're at the very end of this book, pretty much. This is Einstein's Cosmos by Michio Kaku. How Albert Einstein's vision transformed our understanding of space and time. So basically, in this book, we saw the early life of Einstein, how he had kind of struggled in the rigid school system of Germany. And he was somebody who always wanted to use his imagination. He was very imaginative, very creative thinker. And I'm going to sleep. I have notifications turned on. Thank you. Thank you so much. So he actually had some trouble. It's not that he was a bad student, but he did have trouble within the school system and the rigid style of schooling in Germany. And he actually had more of a better time in some place like Switzerland. So we saw somehow sort of how his career progressed. He had some struggles, but then he seemed to do better in Switzerland. And then he met his first wife as well during his schooling, and they got married. They had kids, but then he ended up in Berlin. He ended up meeting his second wife, who was also a sort of a cousin actually as well, and ended up splitting from his first wife. And then basically he got a job in a patent office, because he was actually kind of struggling in his career as an academic. But he did start a study group, and that also helped him a lot. Which countries offer the best aviation course? Hmm, I'm not sure, but probably the US. I'll just go with the US. I don't know, though. I could be wrong, but I think the US has a lot of aviation options. Um, I mean, we have the best Air Force as far as I know. So, yeah. BJ, hi! Hello to South Korea. Hi. Um, okay, so I'll keep going with what I was saying from the book. So we saw kind of Einstein's life developing, and then also we saw that he actually did not he for him to get a job in academia was not super straightforward. It was actually kind of a struggle. So he worked at the patent office, but then he kept in touch with what was happening in the world of physics, in the world of academic science and physics research, and he also had a study group. And that really helped him. He would sound off his ideas off of his colleagues or ex colleagues or sort of the students that people who were students with him, back in the day, and also within his study group. Baji looks cozy. Yes, he's very cozy. Very, very cozy indeed. So I wanted to highlight that because it's basically, even if you don't have a career in academia, kind of keeping up with the research and keeping up with other people who can also kind of give you ideas, as well as exchanging ideas, and having a study group is really important. You can think of this channel and this live stream as a study group as well. We can exchange ideas here and kind of keep each other up to date. So that's really important. And he also understood and kept up with the literature of the time and what was happening. So once, like for example, there was this big confusion and people thought that we would need something called ether for light to propagate to us from faraway objects. And Einstein's work in special relativity made it so that we didn't really need this ether. But if you didn't keep up with the literature and the research that was being published at the time, given that he didn't really have a purely academic career yet, if he didn't keep up with what was being published and what was being done, then he wouldn't be able to contribute. So that's what I'm trying to say. When you're passionate about something, it's important to keep up to date with what is happening in that field and who is doing what in the field. And so not only was he keeping up, he also understood what was being published, and he thought about it a lot. He thought about it deeply. It might have even helped that he's had sort of a boring job, because then that gave him a lot of time and space and energy to think about the problems that he wanted to think about. So that ended up being what helped him, and also he was very interested, of course, in all of this. And in 1905, he had an extremely productive year and gave us the special theory of relativity, space-time, which entailed space-time being relative, mass energy equivalence. He also contributed the photoelectric effect and Brownian motion. So those four things he published about in the year 1905. So just in that one year was an amazing year full of riches from Einstein, as well as there was a lot going on in that period of time. It was a really rich period of time, the early 1900s, as well as well into the 20s and 30s. So we kind of see the developments in physics during this period in this book, including, of course, all of this relativity stuff from Einstein. And not only did he do special theory of relativity, as soon as he kind of finished that up, and he realized that special theory of relativity, of course, gives you the nice theory of light. It takes electromagnetism that was formalized by Maxwell and draws from it this more insight about light and how the speed of light is a constant of nature, and that nothing can go faster than the speed of light, and even in different situations the speed of light is a constant. So basically he was able to draw all these fundamental insights that from the work that had already been done, especially by someone like Maxwell and also Faraday and other people who had contributed heavily to electromagnetism. But to take electromagnetism and draw from it this deep insight and further produce something like special theory of relativity to give us the more updated theory of light as a wave, as an electromagnetic wave, was something just completely remarkable. And also, of course, it gave us the relative nature of space-time. So then, and also it gave us mass energy equivalence principle. So this is all E equals mc squared, if that's probably an equation that most people know about. And also, by the way, that led to later on the atomic bomb. Somebody else actually realized that Lise Meitner, actually in Germany, a Jewish scientist, before she fled Germany, realized that this missing mass was because this missing mass, when they were working on the atomic bomb there, was because of E equals mc squared, and it was to be expected. So anyway, it had this other different, I guess, practical and kind of dangerous application in the form of the atomic bomb later on. That wasn't really the intent, of course, when this is coming out. But basically, these two things, space-time relativity, this relative nature of space-time, and the mass energy equivalence, both come from special theory of relativity. And then he also worked on photoelectric effect, which is, by the way, the old quantum mechanics, because from the same person who gave us something about light, a more sort of wave nature of light, the person, special theory of relativity, gives you a deeper insight into what light is as an electromagnetic wave. But then the same guy, Einstein, also gave us the particle nature of light, and found gave us this concept of quanta of light, or a photon of light, and the particle nature of light is what goes to give us photoelectric effect, getting, for example, something like solar power. When you shine light of a certain frequency on a metal, you might get an electric field or electric current coming out of it, and those two things will be related. That is the energy or the frequency of light that was used, and the energy of the current that you get out. And those were shown and demonstrated in the photoelectric effect. This is what he got the Nobel Prize for, by the way. So later on, when he was finally given a Nobel Prize, Einstein, he was sort of a, because he was primarily known for relativity, and relativity was something that a lot of people didn't really understand. I think people were kind of afraid to give him a Nobel Prize, but eventually he did get the Nobel Prize, but for a much more safer topic, I think, in the form of the photoelectric effect. But still, that is also a very useful, theory and application of physics that we use even now. So, those were what happened in the early 1900s. And then later on, he also worked on general theory of relativity, which is, of course, the more updated theory of gravity and gravitation. And because he worked on special theory of relativity, and that was true for inertial frames, he's also the first one to realize that, well, that's not enough. We need a more general theory of relativity, which would be good and which would work in all kinds of situations, even the accelerating frames and gravitating frames. So that led to general theory of relativity. So along with all of this, there were also developments happening in quantum mechanics, especially in the 1920s and 1930s. Some of these developments were quite bizarre, and a lot of people, some people didn't even, they were so uncomfortable by what was coming out and what quantum mechanics was becoming, that even some of quantum mechanics's old contributors or original contributors almost felt like it's too crazy and they don't want to be part of it. But that's how it was. And so Einstein is considered one of the old or original contributors, because he gave us quanta of light, or photon, the particle nature of light, which is a type of quantum as well. And then there were people like Niels Bohr, the Copenhagen school of thought, as written about in the book here that we've been referencing.
And he even had a very famous debate with Niels Bohr. Um, it's a long time ago. I think it was, I forget the year, it was maybe 1931 or so. Uh, they were debating each other about quantum mechanics, mainly the issue that some of these more classical physicists had with quantum mechanics was its probabilistic nature, the fact that you now dealt in probabilities instead of deterministic physics, like what people were used to in classical mechanics or Newtonian mechanics. Um, you know, quantum mechanics gives you the wave equation of matter, gives you actually the probability of finding a particle like an electron. It does not give you the electron. So probability of finding the electron makes it so that this dissipative wave thing makes sense and it's all good and the math works out, and it fits with reality and experimentation, because we know that the electron of a hydrogen atom, stays sort of close to the nucleus. It doesn't go off into space forever. So at first, when Schrodinger, a very big contributor of quantum mechanics in the form of writing down, for example, he wrote down the wave equation of matter, or a quanta, or a particle. He thought he wrote down the wave equation for a particle, but actually later on, I think it was Max Born who said that it was actually the probability of finding the electron that he had written down, which is given by that wave equation, not the position of the electron. So anyway, things like that. Probabilities also led to uncertainties, and Heisenberg came up with the uncertainty principle, the uncertainty of nature, not the uncertainty of making a mistake and having error in experimentation like one might expect in normal physics, but this was uncertainty as in, this is the uncertainty principle. You cannot measure nature beyond this level of uncertainty, because when you shine a photon on an electron, you change its position, so you can't know both its position and momentum at the same time. There is an uncertainty, and that uncertainty was formalized with an equation by Heisenberg. So all of this type of development in quantum mechanics, the probabilistic nature of it, the uncertainty of it, was very disturbing to a lot of traditional physicists, and even some of the people who contributed to the quantum mechanics themselves. But life goes on. It was shown to be basically very successful, and proved with experiment, and people could take a look at atoms and they saw, yeah, it makes sense. They can't really come up with anything better anyways, but it led to certain philosophical questions. We talked about the spooky effect at a distance, and the fact that, like, if a tree falls in a forest and nobody sees it fall, then does it mean that, what happened to it? Does it not exist? And all this stuff about really the quantum states. There are many possible states of something, and as soon as you make an observation, that determines sort of the state that you observe. The observation itself changes nature and reality. For me, I don't mind some of these philosophical difficulties, because as long as quantum mechanics gives us a way to do the mechanics of the very small and of particles, subatomic particles and the like. Hi, John. You're here. Yay. As long as quantum mechanics handles physics of the small, I'm happy, and I think Niels Bohr was happy. But some of the other physicists were not so happy, and they tried to poke holes at it, including Einstein. So anyway, but quantum mechanics still stands. It's one of the most successful, developments, actually. It's continued to grow, and even with or without problems, people have had to kind of accept it and keep it, take it in their stride. But anyways, all of that was happening sort of in parallel with some of Einstein's efforts. This book is very focused on Einstein, so that's why I mention Einstein so much. And also, Einstein has given us a lot of contributions. So, studying what he contributed in itself is sort of course. So why not, right? Why not study that? The big thing also to mention is that Einstein and some of his friends were actually trying to come up with the grand unified theory, a more formally a more general theory, grand unified theory, which would give us electromagnetism, relativity, and also give us quantum mechanics. Like they were hoping that they can come up with a more general, more bigger theory from which quantum mechanics can just like fall out, and not fall off, fall out, as in as a result of it, so that you didn't need to formalize quantum mechanics in the way that it was currently formalized. These people really did not like the probabilities and the uncertainties way of formalizing the physics of the very small. What they wanted to do was have a more general theory, which would first of all make unify electromagnetism and gravitation. It really irked Einstein that there was sort of a force, the electromagnetic force, which is separate from gravitation. He wanted something to be able to explain those things in a more unified way. And also because all of the quantum mechanics stuff was coming out, he wanted this theory, the same one, hopefully, which comes out of his head and with his colleagues and whatnot. He wanted it all to subsume quantum mechanics so that you didn't need to separately get quantum mechanics out. But at the same time, it was very difficult because quantum mechanics has a ton of observable properties like the spin of a particle, the charge, the mass. All of this stuff would have to come out as well as a result from this theory, and that's not easy. So, anyways, he was not able to unify these things. It was his goal, though, his ambition, and when we read the book, you might see this coming up. And also, superstring theorists have tried to do something like that as well in the unified. So when we read about superstring theory, you might get some flavors of this unification effort, because some of the things that he did get to, for example, one line of thought was just needing more dimensions. If we could describe our reality with more dimensions, then it might help. Was a line of thought at this time during these efforts of grand unification theory. So you might see that come back up in the context of superstring theory when we talk about that. Yeah, what else? So yeah, I wanted to mention these difficulties they had with quantum mechanics. They didn't like it. Higher dimensions, that's something. Oh yeah, they thought that black holes were crazy and could never be observed, but then actually turns out black holes are very real and were observed. So there were three dark things: dark matter, dark energy, and dark stars. Dark energy is something that the first time that the concept of something like dark energy came up was actually when Einstein needed to include what we call the cosmological constant. He called it the cosmological constant. We still have something called the cosmological constant. And he needed to introduce this as an anti-gravity term in his equations, which would go kind of work against the gravity of the universe. And since the universe is not collapsing on itself because of gravitation, he thought we should introduce a term that's kind of keeping everything stable. But actually it turned out that not only are things stable, so to speak, against gravity, but also the universe is not only not collapsing, but it's actually expanding. He just wanted everything to be nice and balanced, but turns out because of this mistake, we actually got to something even bigger, which is the need for what we called dark energy, or the energy of vacuum. So this type of thing, actually he gave us that. But at that time, it was part of a sort of a mistake, in the sense that he thought that the universe would be stable and nice and good with just being able to balance gravity. But now it's almost like you make a mistake, but the mistake is not only correct actually in a different way, but it's almost too correct. It's correct in the other direction, where now we know that the universe is not only has something that fights gravity, but it's also expanding. And not only is it expanding, its expansion is accelerating. So we've gone very much in the other direction now, but the cosmological constant came also from his work. Hi, Anna. Thank you. Fascinating. Yes, this is all very fascinating indeed. Uh, this is like my favorite topic, other than kitty cats, other than my children that I birthed who are kitty cats. So basically, this is dark energy. This thing that he did, this math that he did Einstein, in order to, and this is, by the way, something that he had to face in the same way that Newton had to face things. When Newton gave us the laws of gravitation, which, by the way, are still correct to some degree, Einstein's general theory of relativity is simply a more updated um, theory of gravitation. It's considered the more correct theory of gravitation because it's more generally correct. Newton's is a subset of that. So Newtonian mechanics, Newtonian gravitation works just fine in the scale of classical scales like you and me, human beings, cars, trucks, roads, cats, moon, earth, planets, comets. It works just fine. NASA uses those equations even now. It's fine. But if you're going close to the speed of light, and if you are small, very small, subatomic, then you might need some corrections and some updates. Um, and for that, general theory of relativity is the better, more correct, more updated theory for gravitation. A lot of people don't want to deal with it because general theory of relativity's math is more complicated and you need to be comfortable in a different kind of notation. It's almost like learning another language that it's almost like if you know English and Latin, uh, most of the time English is fine. Latin is, I don't know, it's not a very good example, but it's kind of like if one is good enough, then that might just be fine. You might not need to learn this one. That's what general theory of relativity is. A lot of people don't actually need to learn it, but you should learn it if you're gonna want to contribute to the grand unified theory, for example, as an example, just saying. Or if you want to do cosmic scale type of physics, like cosmology. So at cosmic scales, it is supposed to be the more correct and more updated theory, just so you know. So when he was doing this, just like Newton had to face it, because Newton also was faced with this, because Newton gave us gravitation back in the day. It's a force, it's an attractive force. It's an attractive force. And now Newton gave us also the concept of a force. Force is not necessarily something that, you know, you, force is not really something in Einstein's theory. Einstein gives us sort of the bending of space-time. It's the curvature of space-time way of thinking. That's how Einstein thinks about gravitation. Newton thinks about it as an attractive force between massive objects. So, but either way, both people had to face one thing, which is the universe obviously has matter. Matter has this attractive force between them. According to Newton, it's gravitational force. According to Einstein, it's this bending of space-time, the curvature of space-time. And the more massive something is, the more it will bend space-time. But why doesn't the universe just collapse on itself eventually? Why are we able to be stable? So he had to kind of answer that. And in his equations, he put in a placeholder term to kind of go against gravity. Sometimes it was called anti-gravity, or because it was just a placeholder term, he called it cosmological constant. We still call it cosmological constant. It has a lot more importance now because now we know about this acceleration of the universe, and it's become gravely important to understand the physical nature of what we now call dark energy. But this dark energy concept is as old as that equation writing, is what I'm trying to say. It's 100 years old at this point. So right now, today's date, the two most top questions are nature of dark energy and nature of dark matter. Both are still mysteries, and to understand how to solve these, we must learn everything that happened before that. So that's why we're talking about this. But anyway, dark energy, this concept comes from his work with that anti-gravity need in his equation. Since then, of course, we have a lot of efforts to understand dark energy. All these better instruments and better ways to measure things and better ways to observe the universe also gives us a better sense for a lot of these things. Um, for example, so I would say the biggest thing that has changed between 100 years ago and now is our much better capability to observe, experiment, and instrument nature, and the money we spend on these things to do more of that. So that has changed by leaps and bounds. But as far as paradigm shifting, nature understanding, big insight, we don't really have too many of those in the recent times, as much as we did in the 1920s and 1930s and 1910s or even 1905. Just the one single year of 1905 probably changed physics more than what we have changed probably, I don't know, in the last many years. So very rich time, that particular time, up before World War II. Of course, during World War II, all the scientists were asked to work on the atomic bomb. Not very exciting, honestly, but a lot of people find war to be an interesting topic, so we also covered that. There's an entire chapter on that here. We already covered it. Sad stuff. They dropped 2 bombs on Japan when the scientists probably just wanted to do a demo bomb. And even the people who were in charge of the atomic bomb in Los Alamos probably just thought it would be a demonstration, not an actual, killing of people. But anywho, that's war and that's politics. It's really beyond my pay grade here. But long story short, there were a lot of scientists involved in that as well in the World War II era. And then, of course, there was the Cold War that also affected some things. But basically, since that time of quantum mechanics having a lot of progress, now we also have an entire domain called particle physics. We have the standard model of particle physics. We will get into those topics too. So fear not. We will be getting into more 21st century topics as well. We won't just talk about 20th century physics on the channel, but we should exhaust the 20th century physics topics so that we have a good background behind us. So what's going to be more the highlight in 21st century is going to be the instruments, way better experiments, way bigger experiments, way better ability to measure things more precisely. Something like we will talk about the particle physics, standard model particle physics, as well as beyond standard model of particle physics. So those are the more 21st century things. And of course, we have more direct evidence of something like the gravity waves. So let me read about that. So very importantly, this general theory of relativity, why is it so successful? Why is it considered such a big deal? Because Einstein gave us this in the early 1900s. By 1914, 15, by 1920 or so, or maybe in the 1920s latest, we had general theory of relativity from Einstein. But it was such a profound theory and so difficult. Some of the confirmations of it did not come until much more recently, actually. So gravity waves were only indirectly measured until about, within the last 10 years. So even 100 years after Einstein gave us general theory of relativity, we're still kind of confirming some of the aspects of it, which is really fascinating. And so far, so good. It confirms what he predicted. So that's a huge success of GR, general theory of relativity. I would say, again, though, keep in mind that we don't know what is dark energy and we don't know what is dark matter. So those progress in those directions would be really good as well. Just, keep in mind what we know and also what we don't know is my idea here. We will cover the things that we know and the things that we have learned, but we will also keep in mind that there are big gaps and big mysteries. As we learned more and more, over time, we've also unearthed big mysteries, and that will also be a part of our efforts here. So let me read this part. Um, so they got the indirect measurement of gravity waves from a system called PSR 1913 plus 16. It's a double neutron star about 16,000 light years from Earth, in which two dead stars orbit each other every 7 hours and 45 minutes, releasing copious quantities of gravity waves in their wake. Imagine, for example, stirring a pot of molasses with two spoons, each spoon rotating around the other. As each spoon moves in the molasses, it leaves a trail of molasses in its wake. Similarly, if we replace the molasses with the fabric of space-time and the spoons by dead stars, we find two stars chasing each other in space, emitting waves of gravity. Since these waves carry energy, the two stars eventually lose energy and gradually spiral. It's called Einstein's Cosmos by Michio Kaku. Gradually spiral together. By analyzing the signals of this double star system, one can experimentally calculate the precise decay in the orbit of the double star. So the nice thing about the binary systems of neutron stars, or even if you found a binary system of black holes, binary system of white dwarfs, or a neutron star and a black hole, black hole, neutron star, neutron star, neutron star and a black hole, for all of these systems, pretty much as they orbit around each other, they're actually emitting gravity waves which carry energy away from the system, and eventually such a thing will spiral together towards each other. It's sometimes called a dance in nature, and eventually they collapse onto each other. Okay, so you can try to measure the gravity waves from that collapse, or you can see how the orbit is gradually getting shorter and shorter and shorter. And by measuring this shortening of the orbit, that would be an indirect measurement of gravity waves, because basically the gravity waves are carrying the energy away. Now, in later times, in the last 10 years or so, we also have results of direct evidence, direct measurement of gravity waves, which is really exciting. It happened during when I was still in school. So it's really something. As expected from Einstein's general relativity theory, the two stars came closer by a millimeter every revolution. Over a year, the separation of the stars decreases by a yard in an orbit that is 435,000 miles in diameter, which is precisely the number that can be calculated from Einstein's equations. In fact, the two stars will completely collapse in 240 million years only, owing to the loss of gravity waves. So sometimes we can look back in time and actually see a collapse, and then sometimes the collapse, the way the light we're getting at the moment is when the stars have not collapsed yet. So it really depends where you're looking, in what epoch of the universe you're looking. This precision experiment can be reinterpreted as a way in which to test the accuracy of Einstein's general relativity. The numbers are so precise that we can conclude that general relativity is 99.7% accurate, which is well within experimental error. So they did this back in, this was in 1993. So in 1993 already, which is of course long after general theory of relativity was worked on by Einstein and predicted by Einstein, but it wasn't until 93 that this was the indirect evidence of gravity waves was found with experimentation. That's what I was saying earlier, is that even though we had these great theories and these amazing works coming in the 1900s, early 1900s, that is, like the 10s, the 20s, the 30s, a lot of experimentation type of progress was not until much later, more recently in our type of lifetime, in say the last 10, 20, 30, 40 years, is when we have really made a lot of progress in being able to observe, measure, experiment. And so now we can confirm these things that we could not confirm before. So now we talk about the direct measurement of gravity waves. More recently, there is intense interest in a series of far-reaching experiments to observe gravity waves directly. The LIGO, Laser Interferometer Gravitational Wave Observatory. This is LIGO, God's equation. Yes, this is LIGO. This is the result that I'm talking about that came out as a press conference. It was a very big deal when I was still in grad school, and this is the direct measurement. So Michio Kaku is writing about this in the past before LIGO's result came out, but it's still a good paragraph to read. Project may soon be the first. It is already now the first to observe gravitational waves, perhaps from black holes colliding in outer space. So they found black holes, the same kind of binary, but with black holes, which would of course make bigger gravitational waves, which we could measure here on Earth. If you want to measure them on Earth, of course, you want it to be sort of more bigger, more exotic. If you put the instrument in space, then maybe you can collect gravity waves from smaller events. But LIGO is a physicist's dream come true, the first apparatus powerful enough to measure gravity waves. LIGO consists of 3 laser facilities in the United States, 2 in Hanford, Washington, and 1 in Livingston, Louisiana. It is actually one part of an international consortium, including the French, Italian. Ooh, hi. Hi, thank you, Budsville. Thank you. Beautiful cat, thank you. It is actually one part of an international consortium, including the French-Italian detector called Virgo in Pisa, Italy. You might have heard of Virgo. A Japanese detector called Tama outside Tokyo, and a British-German detector called Geo 600 in Hanover, Germany, although LIGO's final construction cost will be around $292 million plus $80 million for commissioning and upgrades, making it the most expensive project ever funded by the National Science Fund. I don't know if it's the most expensive. I feel like Ice Cube is really expensive too, so don't quote me on that. Quote Michio Kaku. The laser detectors used in LIGO look very much like the device used by Michelson Morley at the turn of the century to detect the ether wind, except that laser beams are used instead of ordinary light beams. A laser beam is split into 2 separate beams that move perpendicular to each other after hitting a mirror. These 2 beams are then reunited. If a gravity wave were to hit the interferometer, there would be a disturbance in the lengths of the paths of the laser beams, which could be seen as an interference pattern between the 2 beams. So with that interference, to make sure that the signal hitting the laser apparatus is not a spurious one, laser detectors are required to be distributed around the planet Earth. Only a huge gravity wave, much bigger than Earth, would be able to fire the detectors all at once. So they have to also pick an event that would create such a big gravity wave. So there is that. Eventually, a series of these laser detectors will be placed in outer space by... Oh, that's right. So we talked about LISA last night. The space... NASA will launch 3 satellites called LISA, Laser Interferometer Space Antenna. Hi, Fuji. They will orbit around the sun at approximately the same distance as the Earth's orbit, miles on a side. The system will be so delicate it will be able to detect vibrations of 1 part in a billion trillion, corresponding to a shift that is 1/100th the width of a single atom. That's how precise it needs to be, allowing scientists to detect the original shock waves from the Big Bang itself. If all goes well, LISA should be able to peer to within the first trillionth of a second after the Big Bang, making it perhaps the most powerful of all cosmological tools to exploring creation. This is essential because it is believed that LISA may be able to find the first experimental data on the precise nature of the unified field theory, the theory of everything. I looked up that LISA is going to launch maybe in 2035. There were some issues with its funding, and it's a lot of people's decision together that they have to agree on. So I read last night on Wikipedia that it's now planned for 2035. So there's no LISA yet. It would have to be launched. I mean, NASA can help them do that, but yeah, the whole funding of it and the agreement of it by European Space Agency along with other people, that had to be worked out, and I think they figured it out to be something that they plan for 2035. Yet another important tool introduced by Einstein was gravity lenses. So we just talked about gravity waves, something that Einstein predicted.
It's still hypothetical device. Yeah. Thank you, Heike. Thank you for being here. Are you gonna stay? And sorry about the volcanoes. You said that Finland has volcanic eruption now. Hope everything is okay. Happy weekend to Baji and science friends. Hi. You're saying hello to Baji, right? Nicholas, how are you? Heike, are you gonna stay or are you leaving? Oh, I'm sorry, Iceland. Oh, okay, sorry. Did you write Iceland? I must have been thinking about Finland. Sorry, that makes a lot more sense. Iceland volcano makes a lot more sense. I was like, wait a minute. Okay. You were there? Thank you. Please do keep watching. Hi, Smile. Thank. Heike, are you gonna stay or not? Thank you, anyways. I love reading your comments later on. Okay, so next we go on to gravity lenses. So this is another tool given to us or introduced by Einstein, and very important tool in astronomy. Gravity lenses, where we can use a heavenly body or a massive object as sort of a tool, giving us an idea. Wait a minute, giving. Actually, I'm just going to read the paragraph before I say something. Oh, what is this? Yet another important tool introduced by Einstein was gravity lenses. Back in 1936, he proved that nearby galaxies can act as gigantic lenses that focus the light from distant objects. So galaxies can act as gigantic lenses that can focus the light from distant objects. It would take many decades for these Einstein lenses to be observed. It would take, yeah, the first breakthrough came in 1979 when astronomers observed the quasar Q0957 plus 561 and found that space was being warped and acting as a lens to concentrate light. So in 1988, so 88, pretty recent, sort of, the first observation of an Einstein ring was from the radio source MG 1131 plus 0456, and about 20, mostly fragments of rings, have been observed since then. In 1997, the first completely circular Einstein rings were observed with the Hubble Space Telescope, my favorite telescope, and Britain's Merlin multi-element radio-linked interferometer network radio telescope array. By analyzing the distant galaxy 1938 plus 666, they found the characteristic ring that surrounded the galaxy. At first sight, it looked artificial, and we thought it was some sort of defect in the image. But then we realized we were looking at a perfect Einstein ring. Oh my gosh. That's awesome.
Said Dr. Ian Brown of the University of Manchester, astronomers in Britain were elated by the discovery, declaring it's a bullseye. The ring is tiny. It's only a second of an arc, or roughly the size of a penny, viewed from a distance of 2 miles. A penny viewed from a distance of 2 miles. Gosh. However, it is a verification of Einstein's prediction made decades ago. So I believe, am I wrong? Gravitational lensing gives us mass of the galaxies, right? So I think it's we will confirm this later on from the book, but it's a very important tool in astronomy. So gravitational lensing as a prediction and then being confirmed with measurement is very important in astronomy because it helps us to do further astronomy. One of the greatest explosions in general relativity has been in the area of cosmology. So we're moving on to cosmology now. Actually, let me take a little break and give you something from the book as well, because I said we would mix it up. So I mentioned, so 1 second. This is, by the way, another book. I said it's introduction. It's actually Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. I got this book for free from the author herself, Barbara, who said it's a very good book to have. According to the author, she said that she can give me the book for free if I let her autograph it. So of course I did, because this book is quite expensive. Let me see how much it is. It's a textbook, so it's probably $1 million. But this is a staple textbook that people have to study from in when they study astronomy or astrophysics. Nicholas says outer space is so interesting. Yeah. Let me just look something up real quick before we move on. I'm sorry. There it is, 443. Going to page 443. We can do that right here. Yeah, we will actually read about that soon here, because event horizon, meaning with black holes, and black holes are a stellar remnant. So that's why I got this book out. We will actually read about that soon here. Okay, good to know about your interest. We will cover this in just a second, actually. Hold on. So yeah. I wanted to look up gravitational lenses in this book from the appendix. So from this book, and this is a textbook, so it's a bit more comprehensive for our knowledge. So that's why I wanted to give you this, okay? One of the predictions of the theory of general relativity is that massive objects can bend the path of light, and early experiment support for general relativity came in the year 1919. Remember that solar eclipse that we read about? That's what this is talking about. When observations of stellar positions during a solar eclipse revealed that the sun had bent the path of the starlight by an angle consistent with the predictions of Einstein. Because massive compact objects bend light, they act as lenses, making distant stars appear higher in flux than they ordinarily would. Higher influx, more influx than they ordinarily would. Gravitational lens, as in like something that makes something bigger. Got it. They act as lenses, making distant stars appear higher in flux than they ordinarily would. Suppose that a compact object, the lens. So the compact object is the lens. Moves directly between us and a distant star, the source. As the lens moves towards the source, as seen from our viewpoint, the flux of light we receive from the source grows larger. As the lens moves away again, the flux decreases to its original value. Thus, the light curve of the source shows a characteristic rise and fall. If the lens is a stellar mass Mako, massive compact halo object, Mako as in an acronym, and the source is a star in the Magellanic Clouds, for example, then the rise and fall typically occur over the course of a few weeks. Yes. Yes, how did you know? Yes, now we are reading about gravitational lensing from Barbara Ryden and Bradley Peterson's book. Just to give you the proper definition, okay? Because I read about it from the Einstein's Cosmos book, but that book is not a textbook. So I just wanted to give it to you from the textbook. So, although lensing events have been seen, there turn out to be fewer Makos than are needed to contribute all the dark matter. Only around 20% of the dark matter in the halo can consist of Makos. There's still plenty of room for WIMPs in the galaxy. Got it. This is a different discussion. We will get into dark matter later, but the author I wanted to just give you the textbook definition of a gravitational lens. And gravitational lenses were predicted by Einstein, and they were also found in the year, what was it? In the year, yes, it is possible. In 1988. So as recent as 1980, the 1980s and 1990s, we are still getting some of these predictions coming true in the form of experiment, right? Okay, so that was gravitational lens definition for you. Now, because we have mentioned neutron stars, white dwarfs, and black holes, I thought that I will also give you some definitions from this book for those types of things. These are extremely interesting objects, and some of you have also asked about black holes. So let's read about that, okay? This is still this book, Foundations. So this is a great book for learning astrophysics. It's called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. So you know that we're using a proper textbook now. This same textbook is used in actual formal classes of students who take astrophysics. So it's not just that you're getting some weird information. This is all good information, okay? These people teach these classes for a living. So the life history of a star. So we are now reading a little bit from chapter 18. It's called Stellar Remnants, page 409 of this book. Basically, as it turns out, white dwarfs, neutron stars, and black holes are stellar remnants, or the form of a star when it's died. So stars, when they are alive, like our sun is alive, thank goodness, as a star, basically there's two main things going on in a star. There is gravitation. A star could just have gravitation, then it would collapse on itself and become a remnant star. But what makes it keep on going is, quiz question, how does a star keep burning? I'm asking you guys. Quiz question, how does a star keep alive? How does it keep burning? Why does it not collapse under gravity? It is because of Someone give a try? Heike? Anybody? How is the sun burning? Anybody? Nobody? Because of which? Yes! Yes! Thank you, Anna. Thank you. Nuclear power. Yes, the sun is making helium out of hydrogen. It's the main nuclear energy, nuclear type of interaction going on in the sun. It can also do other things, but mostly it is fusing hydrogen to make helium. This nuclear power, nuclear energy, is what keeps the sun burning and keeps the sun sunning. And we have a sun and we have energy. It's all because Anna got it. Anna got it. Anna, you win the prize today. Gold stars for Anna. She got it. Yes. Awesome, awesome, awesome. So Anna is correct. The opposing force against the gravitational force of the sun, because the sun could just collapse on itself, a star could just collapse on itself, but what keeps it going and keeps it in a star form is nuclear fusion. It is making a heavier element from something like hydrogen, for example. It can make heavier and heavier elements depending on the age of the star and what cycle of its life it is in. But yes, this is extremely important. If you don't know what is powering our sun, it is nuclear fusion. It is a nuclear power type of thing that is keeping us alive. So please do take that away from this live stream. That's extremely important to understand. Now, when a star is towards its end of its life cycle, it actually ultimately runs out of nuclear power because it makes enough elements that are stable enough to where it is not going to keep on making more and more and more heavier elements. It may reach a more sort of stable state. It can also depend on its what we call stellar abundances. That's another whole chapter. But pretty much when gravity kind of wins and the star is kind of running out of its nuclear power, gravity will win and the star can collapse on itself, and that itself can cause a very big explosion. It is called a supernova, sometimes a hypernova, depending on how big the star was. If it was a very massive star, which our sun is not really even that big of a star. Again, thank God, we don't really want such a big star anyways. I don't think we would be here probably if that was the case. But anyways, the point is that the point is Anna got it. Amazing. So basically, we will talk about the life cycles of a star as well. But for this chapter, what is important is the star can die. Just like anything else, the star can die, and its dead state is what we call a stellar remnant. This is a dead star, which is no longer doing any nuclear fusion, or mostly it's not doing any nuclear fusion. It's not burning. It's not like the sun. It's not really starring anymore. It's a remnant star. And there are three different possibilities for a star when it's died and becomes a remnant. And those are white dwarf, neutron star, and black hole. And we will read about the formal definitions of those here. Okay. The life history of a star is determined primarily by its mass. If you know a star's initial mass, you know, at least in broad outline, how it will evolve. Other factors like the star's initial chemical composition and initial angular momentum have a smaller effect. For instance, the fusion history of a star depends on its initial mass, All mass limits below are approximate. So they give us some mass limits. These could be, in astronomy, pretty much people always compare everything to our sun because, of course, it's familiar. So if solar mass is m solar, then if the mass of the star in question is much less, if it's much less than 0.08, say solar mass, then it would have no fusion. The center of a low mass ball of gas never becomes hot enough for hydrogen fusion. This mass range represents not stars, but brown dwarfs or of spectral type L and T. We will understand spectral types later on. If the mass is between a half solar mass and bigger than 0.08 solar masses, then it will fuse hydrogen into helium. The center of the star never becomes hot enough to fuse helium to carbon and oxygen. Stars in this mass range are M stars on the main sequence and will eventually end up as white dwarfs made of helium. So these stars are still smaller than the sun. And if the star's mass is sort of greater than half a solar mass to 5 times the solar mass, then the fusion will be from hydrogen to helium, helium to carbon, and carbon to oxygen, or sorry, hydrogen to helium and helium to carbon and oxygen. The center of the star never becomes hot enough to fuse carbon and oxygen to heavier elements. Stars in this mass range are A, F, G, and K stars on the main sequence and end up as white dwarfs made of carbon and oxygen. So isn't this so interesting? It's all based on the mass of the star. And if the star mass is between 5 times and 7 times the mass of the sun, then it will do a fusion of hydrogen to helium, helium to carbon and carbon and oxygen to neon and magnesium. Stars in this mass range are B stars on the main sequence. Our sun is also on the main sequence, of course. And then if a star is greater than 7 times the mass of the sun, then it will do fusion of hydrogen to helium, helium to carbon and oxygen to neon and magnesium to silicon, and silicon to iron and nickel. Stars in this mass range are O stars on the main sequence. Note that the elements produced have atomic masses that are multiples of 4. This is because the heavier elements are built up by fusing on additional helium-4 nuclei. So just more helium getting tacked on to the nuclei. The statement, a star's properties are determined primarily by its mass, is known as the Russell-Vogt theorem, after the ubiquitous Henry Norris Russell and the German astronomer Heinrich Vogt, who were the first to realize its truth. So the fact that the star's mass is the one that primarily ends up affecting everything itself is a big find in astronomy. Hi! Hi, Yash! How are you? Look at Baji. I want to stretch my legs. Ah! Ah! Oh! Oh my gosh. Oh my gosh. My leg is stuck. Oh God. Oh God. Oh God. Oh God. Oh God. Oh God. Okay. Oh gosh. Oh my God, Baji. How are you, Yash? How's it going? We are learning astronomy. All right, everybody. Did you get that? The nuclear fusion stuff and how the star's mass pretty much determines its fate. More massive can mean different types of nuclear fusion and a different outcome for its stellar remnant. So we will keep going. White dwarfs. How do we get something called the white dwarf? A white dwarf is a stellar remnant supported by electron degeneracy pressure. The name white dwarf, as it turns out, is something of a misnomer. Nobody objects to the dwarf part. White dwarfs really are small compared to main sequence stars of a comparable mass. As we computed earlier in the book, the radius of the white dwarf Sirius B is, oh wow, it's much smaller than the radius of the sun, and its mass is comparable to the mass of the sun. Wow. Yes, thank you. So white dwarfs, thank you. Yash says I'm good. Also just came home from school. Baji looks so cute. Oh, so you're all done with school this week then? Yash, Friday done. So white dwarfs are much, much smaller in size than our sun, but can have a mass that's like comparable to the sun. What about you? How are you? Good. Good. You know, we ate a ton of food, doing the live, studying physics and astronomy. Pretty good. It's been raining all day in Boston today. But yeah, so they can be a lot smaller, but kind of have the same mass. However, not all white dwarfs are white hot, although the first discovered white dwarfs, such as Sirius B, have high surface temperatures. Sirius B has a temperature of 25,000 Kelvin. Some white dwarfs have surface temperatures as low as 4,000 kelvins. White dwarfs are high in density compared to main sequence stars. The average density of Sirius B, well, it's very high. It's like 2 times 10 to the 9 kilograms per meter cubed. Goodness. Which is about 200,000 times the density of lead. So they are 200,000 times more dense than lead. Yep. Oh, good. Wow. Ooh, so because of of them being so dense, where is Suji and Fuji? Let me show you.
Here is Fuji Baba. Shona Shona Fuji. Here is Suji Mama. Shona Shona Suji. See that? Hi. 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 Let me show you her face. Hi. She's taking a deep, deep nap. She's in a deep, deep nap.
Your kitties are awesome. Thank you. My baby logs.
Oh, I'm sorry, Baji. I just wanted to rotate Baji.
So white dwarfs are very dense.
Baji's so cute while laying close to you like that. Yeah.
Thank you. White dwarfs are super duper dense. And what happens is electrons become degenerate when they are packed closely enough that the Pauli exclusion principle, remember we talked about the Pauli exclusion principle when we discussed quantum mechanics, produces an additional form of pressure to keep them apart. The electron degeneracy pressure is a consequence of the Heisenberg uncertainty principle, which states that you can't simultaneously specify the position x and momentum p of a particle to arbitrary accuracy. There is always an uncertainty in each such that delta x, delta p is greater than equal to Planck's constant h bar, which is the reduced Planck constant introduced in section 5.1 of this book. Suppose that the degenerate electrons have a number density of Ne. In their cramped conditions, each electron is confined to a volume very small. Thus, the location of each electron is determined with an uncertainty, blah, blah, blah. And if the electrons are so, we have some equations now for the electron momentum and whatnot. And thanks to the uncertainty principle, degenerate electrons are zipping around with a speed proportional to Ne over 1/3, Ne to the 1/3 regardless of how low the temperature drops. These Heisenberg speeds contribute to the pressure just as the thermal speeds do. So, white dwarfs, in other words, have electron degeneracy pressure, and that's what they are supported by. Oh, they all look so cute while laying close to you. Thank you. Yes, they are cute. They are. Here, I'll put you over here. I will put you over here. So because white dwarfs are supported by electron degeneracy pressure, it's almost like they can't really collapse any further. Because, you know, gravity could have made it collapse further, but that's not really possible because they are supported by electron degeneracy pressure, because Heisenberg gave us the uncertainty principle, and the Pauli exclusion principle says that you can't you can't get packed any closer than this, sir, to the electrons of the white dwarfs, that is. So anyway, we can, because white dwarfs are supported by electron degeneracy pressure, we can derive a simple mass-radius relation for white dwarfs. Warning for the faint-hearted, since we want only the correct proportionality between radius and mass and are not concerned with exact numbers, we'll be omitting numerical factors like pi and 2 from the following analysis. Since a white dwarf is in hydrostatic equilibrium, its central pressure must be... Now there's some equations. So hopefully you get some idea of a white dwarf from all of this. Now there's a ton of equations to aid you in understanding the white dwarf. Ooh, we have the spectrum of the white dwarf, Sirius B now. Pressure broadened Balmer lines. Oh, wow. Wow. So, if anybody asks you, why does the white dwarf not collapse? The answer is electron degeneracy pressure. Ooh, the maximum possible mass for a white dwarf is around 2 solar masses. Look at that. It's called the Chandrasekhar mass after the astrophysicist Subramanian Chandrasekhar, who was the first to calculate it. A more careful calculation of the Chandrasekhar mass for a carbon-oxygen white dwarf yields 1.4 solar mass. Any star that can reduce its mass below the Chandrasekhar mass, generally by strong stellar winds during a giant phase, will end as a white dwarf. It is estimated that stars with mass of around 7 solar mass or less will be able to slim themselves down below the Chandrasekhar mass. This calculation is uncertain, though, since mass loss during the giant phase is irregular by nature and difficult to model. So, you know, during a giant phase, it might lose, stars can kind of lose some of their mass with stellar winds. Stars with initial masses less than 0.5 solar mass will eventually become helium white dwarfs. Stars between half a solar mass and 5 solar masses initially will leave behind carbon oxygen white dwarfs, and stars between 5 and 7 solar masses will leave behind neon and magnesium white dwarfs. So pretty much, depending on the initial mass of the star, you can kind of tell what type of white dwarf it will leave behind, or you can get a pretty good idea. It seems like astronomers know a lot about this, and you can even know the composition of the white dwarf, like whether it's a helium white dwarf or a carbon oxygen white dwarf or a neon magnesium white dwarf. But white dwarf it will be, depending on the mass of the initial star. Sounds like not too big of an initial mass. We're talking 7 solar masses or less for the entire range. And the white dwarf is white dwarfing and not collapsing further because of electron degeneracy pressure. Okay. Now we will talk about neutron stars. Because I said we would talk about stellar remnants and take this opportunity to talk about stellar remnants, which includes white dwarfs, neutron stars, and black holes. I know somebody asked me about event horizon. That has to do with the black hole, and we will get there, so no worries. Neutron stars and pulsars. What happens to stars whose initial mass is greater than 7 solar masses? So we just said that if your initial star mass is back, hi clicker, if your initial star mass is 7 solar masses, our sun, that is solar mass, or less, you're likely to make a white dwarf when you die. But what if your mass is greater than 7 solar masses? There aren't many stars that massive, but they do exist. Very massive stars have short lives and die spectacularly, leaving behind a badly crushed corpse. The main sequence lifetime of a massive star is short. There's an equation for that given to you by the authors if you're interested. Life after the main sequence when the star becomes a supergiant. So after the main sequence of a star's lifetime, it goes through some giant, what they call giant phases. So after main sequence, it becomes a supergiant. And its life cycle will be even shorter after it becomes, like a main sequence star is going to have a long life. Like our sun is on the main sequence. Once a star becomes a giant, it will not have that long to live. The ultra-luminous supergiant is relying on less efficient energy sources. Because if it's, just think about it, if something is super luminous, it's burning out, quite literally. It's like a burnout, you know, working too hard, not taking any vacations, burning out. Fusing hydrogen to helium releases about 6.4 times 10 to the 14 joules per kilograms. Therefore, fusing helium all the way to iron releases only 24% as much energy per kilogram. In its last moments as a star, a massive supergiant has many concentric fusion layers over an iron core. Oh, so cool. We have a schematic diagram. So the central fusion region. So the central, the core is iron. Oh. Then silicon, then oxygen, then neon, then carbon, then helium, then hydrogen. Oh. I love it. A supergiant star, Betelgeuse. We all want Betelgeuse to die, finally. And give us a supernova. Hey, Google, has Betelgeuse died yet?
I don't understand.
All I know is Betelgeuse is supposed to die. A supergiant star such as Betelgeuse can have a radius of over 1,000 solar radii. However, models of stellar evolution indicate that the dense central fusion region of the supergiant, has a radius less than 1 solar radius. The central iron core is very dense, thousands of tons per cubic centimeter, and is supported by degenerate electron pressure. The iron core continues to grow in size as a silicon fusing shell eats its way outward in the supergiant. When the iron core reaches the Chandrasekhar mass, it is no longer adequately supported by the relativistic degenerate electrons. One second. When the iron core reaches the Chandrasekhar mass, it is no longer adequately supported by the relativistic degenerate electrons, and it starts to collapse very rapidly. How come we haven't figured out what dark matter, you mean dark matter is? Can't we just grab a little bit in a jar and bring it back to Earth? No. No. Beetle. Oh, you're joking. Got it. Beetlejuice. Yes. What, Heike? Has it died? I mean, it probably has died. We just don't have the light from its death yet. Or am I wrong? Has it died? Because Beetlejuice is a giant. It's a red giant, right? All right, we'll keep going on the neutron stars. So neutron stars are bigger, or their initial star mass is bigger than 7 solar masses. One side effect of the collapse is thus a huge burst of electron neutrinos. Ooh, neutrinos, my kind of particle. A Chandrasekhar mass of iron contains around 10 to the 57 protons, so around 10 to the 57 neutrinos are created during the collapse of the iron core. Because in the nuclear reaction of the proton, we would get the electron neutrino. This burst of neutrinos escapes from the star, carrying away a large amount of energy. So something I forgot to mention is that during any kind of star event, whether a star is dying, whether a star is evolving, anything, even our sun produces a ton of neutrinos. In fact, the neutrinos that are hitting our body all the time, all those big numbers that people talk about of lots of, what did I just say? I meant neutrinos. Neutrinos, there's a ton of neutrinos that are constantly hitting us all the time. And the ones that are mostly encountered by us are from our sun. So pretty much in any nuclear type of reaction. So sometimes I use the the example of chemical reactions, where you know how in chemical reactions there is always an electron that's involved. In nuclear reactions, there's always sort of a neutrino that is involved. A neutrino is a fundamental particle. It's a lepton. We will get into it later on. But take my word for it for now, it's a fundamental particle. So when these stars are evolving and all these nuclear reactions are happening within the star, it is releasing neutrinos at every step. And if you have a ton of these, for example, protons, and those protons are undergoing some kind of nuclear reaction, that's also that many neutrinos that's being released. And the author is saying that the burst of neutrinos escaping from the star will carry away a large amount of energy. This is very important because it would mean that it would help gravity to win, basically. The more energy is carried away from a star, the more what it will be left with is its massive mass, and it will collapse onto itself and die because of that. ultimately a star's death is gravity winning and collapsing, making the star collapse, and whatever other things, other explosions, other type of energy release that is happening in the star's processes that take the energy away from the star is going to help gravity win more and more. So Heike is saying, oh my gosh, I touched the phone screen. Betelgeuse may have died too far to know red giant light goes here so long time ago. Yeah, it's a red giant and I want to see its supernova. If you was a million light years away, right this moment, you could still see the dinosaurs. Yeah. Hi, Astro. Hi. Hi, Heike. Hi, Nicholas. Hi, Astro. Hi, Anna. Hi, everybody. So, keep in mind about the neutrinos, okay? We will come back to neutrinos later on in a different live stream because I worked on neutrinos. So you will get a plenty of neutrino fill at some point. For now, just remember that neutrinos are this elusive, weakly interacting kind of particle. They're leptons. They are in the same family of particles as electrons, but they do not have charge. Electrons have charge, neutrinos do not have charge. But they're sort of a cousin of the electron. They're a lighter, much lighter, and neutrally charged cousin of the electron, and they are involved, they're very nosy. They're involved in pretty much every nuclear reaction, just like electrons are involved in every chemical reaction. I don't think there's a chemical reaction that can happen without an electron of some kind going somewhere, being nosy. When water is made from hydrogen and oxygen, you know, those things happen. Exchange of electrons and things like that, an addition of molecules together, so atoms together. So atoms together to make a molecule. So just like that's a chemical reaction, just keep in mind that there are nuclear reactions. For example, hydrogen fusing together to make helium, helium's fusing together to make carbon, oxygen, silicon, iron, and in all of these types of nuclear reactions, there is an elusive extra particle that is often released. It's a side product of almost every nuclear reaction, and that is the neutrino. We will learn much more about it later on, but just know that it can carry away, they're very tiny, right? So they can go out more easily. Like the neutrinos from the sun are constantly hitting us and we don't even know. It's fine, it's not too bad because it's just a solar neutrino. Not very high energy or anything like that. But the neutrinos that would be leaving these stars, for example, would carry away a lot of energy. This burst of neutrinos escapes from the star, carrying away a large amount of energy, about 10 to the 46 joules. That's a lot. For comparison, the sun will radiate around 10 to the 44 joules of energy during its main sequence lifetime. Oh, wow. So the sun, during all of the time that we will ever see the sun, which will be a main sequence star pretty much for us, it releases 10 to the 44 joules of energy. And the neutrinos alone from something like a star that is more massive, causing it to become a neutron, the neutrinos alone carry more energy out. The core is now a sphere of 2 times 10 to the 57 neutrons that are essentially in free fall. So basically, what has happened here is a proton plus electron, because there was that there's electrons in the system as well. Basically, the reaction that I didn't show you, let me show you. This reaction happens in the star the proton plus an electron goes to a neutron and a neutrino. So because of that, we have now taken a bunch of protons and made neutrons in the star, and we have also made neutrinos that have carried away a ton of energy from the star, away from the star. So hopefully we can catch some of these neutrinos with our neutrinos with some of these neutrinos with our neutrino telescopes. So don't confuse neutrino with neutron. I hope that I have not been misspelling or mispronouncing those too much, but neutrinos are the tiny particles that carry away energy. So this burst of neutrinos escapes from the star, carrying away a large amount of energy. The core is now a sphere of 2 times 10 to the 57 neutrons, because all those protons made neutrons and also neutrinos that are essentially in free fall. Can anything stop the headlong collapse of the neutrons? Anybody? Quiz question. Can anything stop the headlong collapse of the neutrons? So because a ton of nuclear energy has left the star, its death is certain. It will be collapsing because gravity is winning. And we've made a bunch of neutrons. But can the neutrons keep on collapsing to nothing? No, because of neutron degeneracy pressure. Core collapse can be stopped by neutron degeneracy pressure. Degenerate non-relativistic electrons have a certain pressure. There's the Fermi exclusion principle applies to neutrons as well as to electrons. So we saw about electron degeneracy pressure that's supporting the white dwarf. Now we have neutron degeneracy pressure, because all of those things we learned in quantum mechanics, which tells us that you can't just squeeze some neutrons down to like nothing. That's not allowed. Gives us this. So there is now a pressure. It's from the neutrons. You can't get the neutrons too close to each other. Already they're complaining. They don't like it. They don't like it. But because of massive amounts of gravity and mass collapsing onto itself, the neutrons have already gotten very close to each other and they don't like it. But so there is neutron degeneracy pressure, but that's what's making a stable state for the star, or the star remnant rather, because the star is kind of done. Because if it still had nuclear power left, and if it was still burning and making heavier elements out of the lighter elements, then it would still be a star that's burning and has enough nuclear power to keep going. But if it does not have enough nuclear power to keep going, then it will do all of this other stuff that we're talking about now. So a sphere of neutrons supported by degenerate neutron pressure is called a neutron star. Yay! One more example of a stellar remnant, or what happens to a star when it dies. We are almost there now. Next will be black holes. It doesn't satisfy our strict definition of the star. So even though, remember how white dwarfs are called white dwarfs? So there's no word star in there, but it is a stellar remnant. It's the state of a star after the star has died. Neutron star is not really a star in the sense that it's a stellar remnant. It's after the star has died. It's not strictly a star. Just like a black hole, same thing, stellar remnant. Since a neutron star isn't gaseous and isn't powered by fusion, but the name has stuck. So it got the name neutron star and the name has stuck. But to be a real star, you would have to be gaseous, and you would have to have you would have to be powered by nuclear fusion. Okay, so neutron star, the star is a misnomer. So a white dwarf, you're the star. Me? Oh, thank you. Aw. Fusion, yeah. Aw. A white dwarf, a sphere supported by electron degeneracy pressure, and neutron star supported by neutron degeneracy pressure. And we also learned this very important thing where, because a bunch of protons made a bunch of neutrons, they also made a neutrino in the process. And those neutrinos, when you have a ton of protons making a ton of neutrons and also making a neutrino per reaction, and those neutrinos are those light elusive particles that can kind of just run away from the star, they also carry massive energy away from the star, even reducing its ability to star anymore, and gravity will win. So that's how we make the stellar remnant called neutron star. Thank you, Anna. X is asking, do you believe in heaven? I believe in heavenly bodies like the sun, moon, Jupiter, Saturn, Neptune, Uranus, Pluto. I believe in our solar system and the galaxy and extragalactic objects. If that is heaven, and also a good life is like heaven. So, for one plausible, okay, I think we're good. Oh, let me tell you the mass, or sorry, let me tell you the. So you are godless. You asked about a place, not a god. Heaven, right? Or maybe I just don't know what heaven is. You're godless. I wouldn't say that. Let me tell you. Oops, there. You can be next to Suji. What now? Every god is heaven and hell. Okay. Their alpacs have live about Beetlejuice many year. What do you mean? I'm not following. There is a live about Beetlejuice? Or Beetlejuice will be alive now? For a long time? What are you saying, Heike? Oh, YouTube live. Okay. All right. Good to know. I will look it up. Stay on. Stay there, phone. Okay. So let me tell you the size of a neutron star. Okay. Honestly, I don't want to get into the equations, but a neutron star is very small. It's like 10, 11 kilometers. It's very, very small. What is this? Can you imagine though, a star that was so massive, reducing down to a neutron star, which is like the order of 10, 11 kilometers? That's ridiculous. Since neutron stars are tiny, you might think they'd be difficult to detect in the vast darkness of interstellar space. In fact, there's more than one way to detect a neutron star. So there's a few ways. And the Chandra X-ray Observatory is one of the possible ways. Apparently, neutron stars are capable of creating photons in ways other than simple black body emission because angular momentum is conserved during core collapse. Neutron stars rotate rapidly. Rotation speeds as great as 0.1 c, so 0.1 times the speed of light are possible with the corresponding rotation period of 2 times 10 to the negative 3 seconds. So they rotate really fast because the magnetic flux threading through the core is also conserved during collapse. Neutron stars have very strong magnetic fields. So this is what makes them pulsars. Rapidly rotating, highly magnetized neutron stars are called pulsars. So if they're rapidly rotating and they're magnetized, then they are pulsars. The name pulsar was given not because they pulsate in and out like Cepheids, they don't, but because they produce pulse of electromagnetic radiation as seen from the Earth. So because of that too, we can kind of see them more easily. So there are some ways like that to see the neutron stars or pulsars. Why are we sure that pulsars are rotating magnetized neutron stars? For one thing, we don't know of anything else that would produce strong pulses of light at such short periods. So that's why we think it's neutron stars. If a pulsar were actually undergoing radial pulsations with a period of 10 to the negative 3 seconds, its density would have to be, there's an equation, so it would have to be denser than any known white dwarf. So there's math reasons why we think that they are neutron stars. A clinching piece of circumstantial evidence is that some pulsars are found within supernova remnants. Both neutron stars and supernova remnants are created as the consequence of core collapse in a massive star. So it's a circumstantial evidence that supernova remnants are neutron stars in the cases where the stars were massive enough to make neutron stars as the remnant. So there are more reasons given. It's all good. Next is black holes. We will also read about black holes. And we might come back and talk about neutron stars again tomorrow, but let's go into black holes because I know people asked about that. Neutron stars are not the ultimate. So we just saw that neutron stars are crazy dense. They come from more massive stars than the 7 solar mass limit. They're even more massive than 7 suns, and they have iron cores and a ton of protons make the neutrons, making neutrinos leave the system with a ton of energy, and everything kind of collapses down over by gravity, but they cannot collapse too much because of neutron degeneracy pressure, which is coming from quantum mechanics and exclusion principles. So that's what a neutron star is, and neutron stars are very compact. They're very small in the end. Oh my gosh, what is this? There's a bug. Now we come to the last and final type of stellar remnant, what happens to a star when it dies, which is a black hole. Neutron stars are not the ultimate in compression for stellar remnants. There exists an upper limit to neutron star masses, the Oppenheimer-Volkoff limit, that is analogous to the Chandrasekhar mass for white dwarfs. The upper mass limit for neutron stars is difficult to calculate because the strong nuclear force must be taken into account and gravity must be treated using general relativity. Although there is still some debate among neutron star mavens, an upper mass limit of 3 solar masses is generally accepted for neutron stars. So around 3 solar masses. Like they don't expect a neutron star which has let me just ask Google. Hey Google, what is the radius of a neutron star? Let's see what Google
Between
says.
10.4 and 11.9 kilometers. On the website mpg.de, they say, we find that the typical neutron star, which is about 1.4 times as heavy as our sun, has a radius of about 11 kilometers, says Baji Krishnan, who leads the research team at the AEI Hanover.
Okay. All right. Baji, can you go over here for a second? My leg hurts. So There was an equation earlier which was kind of approximating the mass of the neutron star. And that's why I said it's around 10, 11 kilometers, but I wanted to verify with Google as well, as in what they tell people in general. Because everything, there's an equation for everything in all of this. And if you really want to get down into the details, you'd have to do this yourself, like read the book yourself. It's hard to say it right without showing the equations. I might do a presentation style live at some point where I would be able to show it more. But basically, it's safe to say it's around 10, 11 kilometers. So that's like extremely compact for something that is heavier than the sun. Like our sun, can you imagine how big it is? Right? Like, just imagine the Earth, how big it is. The sun is so much bigger. And then a neutron star is more massive than the sun, but it is very compact. So they came up with some generally accepted upper limits for the mass of a neutron star. It's around 3 solar masses. They're saying it can be much more than 3 solar masses. Stars with initial mass greater than 18, that's 1/8 solar masses, or so will leave behind remnants with mass more than this max mass, which is the 3 solar masses. These ultra-massive, ultra-luminous, short-lived stars will leave behind black holes as their remnants. So if you ask who is going to leave behind a black hole, it's going to be these bigger stars, the 18 solar masses or more mass stars, and whose remnants are going to be more than the 3 times solar mass. So, because just think about it, if a neutron star is like 10 kilometers, 11 kilometers, and it has 1.4 solar mass as its mass in that small compact little region, and its maximum mass can be around 3 solar masses. If you have much more than 3 solar masses, you know, being compact makes for a very extreme environment, and that's only possible at that point. You are now a black hole, because now you know, forget neutron degeneracy pressure, forget electron, those types of physics is now being overcome. So let's read about that. A black hole can be defined quite simply as an object whose escape speed is greater than the speed of light. So if you want to escape a black hole, you have to have a speed greater than the speed of light. So we don't know of things that would escape the black hole. In other words, it's black hole, dark star, because even light does not escape it. The critical radius at which a mass m has an escape speed equal to the speed of light is called the Schwarzschild radius. So this is good because we talked about black holes and Schwarzschild radius already as part of that book. So hopefully this is like a review. So remember how Einstein had written down the general theory of relativity equations sort of approximately, because they're pretty complicated equations. But then Schwarzschild was the first one to write them down more exact and absolutely for a point-like star, remember? And at that point, they only knew of black holes as a theory. They didn't know that, they could not imagine that they could be real. Actually, they thought that was the craziest idea. But actually, black holes are real. It's the one dark thing that's real. Dark matter, dark energy, we don't know what they are, and we don't know, there's still ongoing research, but black holes we have learned a lot more about, and they are definitely real. So yeah, so how they do the math to figure out what are the requirements to be a black hole, I say this, but basically really that's the legitimate way of thinking about a black hole, is like if you want to just say, okay, well, here's the equation, here's the general relativity equation, and I'm just going to make sure that even light can't escape this environment, right? So what radius do you have to be? And then intuitively, you also know that that radius is probably going to be kind of small, especially considering the mass of the black hole, because you're saying something got so dense that it is such a dense ball of mass that it is such a center of gravity, such a center of this extreme environment where even light cannot escape. So what they do is they just equate the critical radius at which a mass m has an escape speed equal to the speed of light is called the Schwarzschild radius, or Schwarzschild, after the physicist Karl Schwarzschild, who first calculated it in a relativistically correct manner. In general, you don't expect Newtonian calculations to give the correct results in the highly relativistic regime. In the case of computing the Schwarzschild radius, however, it works out correctly. Any object will become a black hole if you squeeze it until it is smaller than its Schwarzschild radius. So now, because the Schwarzschild radius is given by 2g, that's the capital G, times m over c squared. Basically, if you put in your mass into the Schwarzschild radius, you will get your Schwarzschild radius as well. So even you could be a black hole, Nicholas. We just have to put in your mass into the Schwarzschild radius equation, and then we can figure out what radius you need to be in order to become a black hole. Any object will become a black hole if you squeeze it until it's smaller than its Schwarzschild radius. An astronomer with, here it is, an astronomer with a mass of 70 kilograms. I don't know if that's your mass or not. 70 kilograms is that like 150 pounds? Whatever, I don't know. 70 kilograms will become a black hole if he or she is squeezed to a radius of 10 to the minus 25 meters. So if you become something like 10 to the minus 25 meters small, then you could be a black hole. While it's not practical, nor in most cases desirable, to squeeze an astronomer to this submicroscopic size, it is practical to squeeze an extremely massive star down to its Schwarzschild radius. Yeah. See, we are small, so squeezing us to be that small, at least in our classical lives, is hard. But if you have a very extreme situation, an extreme environment like the death of a star, and a star is extremely big, right? Then squeezing a star down to its Schwarzschild radius is not so impractical, because it's all, because in that environment it could happen. It does happen, because stars run out of their nuclear power and they collapse under gravity. So just let gravity do the work. For a massive stellar remnant, apparently the Schwarzschild radius is 3 kilometers times mass of that star divided by solar mass. So every black hole is surrounded by an event horizon. So this is what the original question was by Nicholas. Every black hole is surrounded by an event horizon, a spherical surface whose circumference is equal to 2 pi times the Schwarzschild radius. So once you figure out the Schwarzschild radius of your black hole, which is given by this pretty simple equation, then you just times it with 2 pi to get you the sphere around the black hole, which is the event horizon. It is possible to enter the event horizon, but it is not possible to emerge again. So the event horizon is sort of, basically, this math is a calculation. We had to formalize the definitions with a black hole. Basically, it doesn't really matter too much about what is beyond the event horizon. Like if the black hole is here, the event horizon could be here, It just doesn't matter too much what happens here, because once you enter this, you can't really come back out. So it's not really we know anything about it's not like really we understand or would get to see this. That's the point. And so to write down the equation, we just set the equation such that light cannot escape. So we set the velocity or the escape velocity of this from this compact object to be the speed of light. So it's giving you that critical radius, or the critical distance, really, or not distance. It's basically, yeah, you get the critical radius by putting the speed equal to speed of light to say that you cannot escape unless you have speed of light or higher. So since we know that things cannot have the speed greater than the speed of light, as far as we know, we just set the speed equal to speed of light, which gives you the critical radius, because the critical radius could actually be a little smaller too, right? So basically, that's how you get that limit of the radius, the Schwarzschild radius. And then if you just consider a sphere of that radius, then you get the event horizon. So it's possible to enter the event horizon, and it's called event horizon because that's like up to which you can have events. After that, you know, if you're past the event horizon, there are no more events that you can call us about. You're done. So that's kind of, I think, the naming of it and the math of it, which I'm trying to explain here. So it is possible to enter the event horizon, but it is not possible. So just know it is not possible to emerge again, because remember, to get the event horizon, we had to set our escape velocity to the speed of light. And we know that nothing has speed greater than the speed of light. So nothing, not even light, travels fast enough to escape from inside the event horizon. That's when you get into the movie, yeah, Interstellar. Yes, that's when you call daddy from inside the black hole, I guess, and learn where, what's the actor's name? Matthew McConaughey, whatever, right? That's when you call that guy. Hello. Need dad. Matthew McConaughey. McConaughey? Type the name of this guy, please. All right, so general relativity predicts the existence of singularities within event horizons. So it is possible to enter the event horizon, but it's not possible to emerge again. Nothing, not even light, travels fast enough to escape from inside the event horizon. General relativity predicts the existence of singularities. Within event horizons, a singularity is a point of infinite density and infinite space-time curvature. However, to test the predictions of general... Yes, Matthew... Oh, thank you, Heike. Matthew McConaughey. Matthew McConaughey. I like that movie. Prometheus. I haven't seen it. I haven't seen Prometheus. I've seen Interstellar. So remember, general relativity had predicted the existence of singularities within the event horizon. A singularity is a point of infinite density and infinite space-time curvature. However, to test the predictions of general relativity and see whether singularities really exist, you'd have to enter the event horizon of a black hole and call Matthew McConaughey. Just kidding. Presumably, once there, you'd be able to discover the answer, but you wouldn't be able to communicate your results to the outside world. It would be the ultimate scientific tragedy, having a great result, but being unable to publish it. Lurid sci-fi movies sometimes regard black holes as dangerous vacuum cleaners, sucking up everything within reach. In fact, when you are far outside the Schwarzschild radius of a black hole, its gravitational pull is just the same as you'd feel from any other object of the same mass. So black holes are just massive bodies, which, we would feel their gravitation just like any other massive body's gravitation. If you're far outside the the Schwarzschild radius, because we've discovered that there are lots of black holes. There are generally supermassive black holes in the centers of many of our galaxies, many of the galaxies that we know of. So it's no big deal, really, in terms of gravitation. You would just feel it normally. But if you get too close, that's where the problem lies. So just don't get close to the black hole, and especially don't get to its Schwarzschild radius close. What makes black holes potentially dangerous is their extremely compact nature. As you approach the central singularity of a black hole, you feel stronger and stronger tidal forces until you are eventually ripped apart. So just like the moon, gives us tides on Earth for the oceans, same thing. You would have tides on you if you were getting close to a black hole. We can actually calculate these tidal forces, and it's not very comfortable at all. So it would be unadvisable. If you want to spare your friends and relatives the gory side of your demise, you should take care to dive toward a high mass black hole rather than a low mass black hole. For a low mass black hole, you will be ripped apart before entering the event horizon. For a high mass black hole, you will be ripped apart after entering the event horizon. To see why this is, let's review what happens as you drop. So there are equations to, like I said, we had to do these. So I remember I'm getting flashbacks of these tidal forces. I don't know why physicists just love this topic, and they want us to calculate the tidal forces that I would experience if I got close to a black hole, depending on its freaking mass. So let's not get into that. I have already done this in my past. But yes, there are equations to calculate the tidal forces on an object as they got close to a black hole. And whatever, man, it's not that crazy. Black holes ultimately are not that crazy. Now, black holes have been observed. We're good with black holes. So black holes are not that mysterious. We know about black holes. And like there's much more observation. Yeah, that is a theory. Whether black holes is a bridge to another world, that's not been proven. But as far as black holes existing, there is much more observational evidence about that. Okay, let me tell you about, let's see. Let me tell you about Sagittarius 462. Since you ask. So, at the center of our galaxy is a strong radio source called Sagittarius A. So, when there is an object that releases some kind of energy that we can pick up on, then that's an observational, then we can make an observation of that object. So, Turns out that at the center of our galaxy, there is a strong radio source called Sagittarius A. The total region of radio emission, there's a picture that shows that. The spectrum of the radio emission indicates that it is a synchrotron emission produced by relativistic electrons accelerated by a magnetic field. The long prominences stretching away from Sagittarius A resemble solar prominences scaled up by a factor of 1 billion. The early radio observations that detected Sagittarius A were of low angular resolution and merely revealed the presence of an unresolved blob of radio emission. More recent observations have found detailed substructure in Sagittarius A, and if we zoom in on the highest surface brightness region of Sagittarius A, we find an interesting radio source called Sagittarius A West. And Sagittarius A West is a rotating mini spiral of partially ionized gas after 5 parsecs, about 5 parsecs across. Its radio spectrum looks much like that of a hydrogen 2 region in which gas is excited by a central source of ultraviolet light. In the case of Sagittarius A West, the central source must be very luminous. But what is it? If we zoom in on the center of Sagittarius A West, we find a highly compact radio source called Sagittarius A star. Sagittarius A star would fit inside the orbit of Jupiter and is smaller than the star Betelgeuse. Oh my God. Don't look for a footnote, the asterisk is part of the name. Sagittarius. I did look for a footnote. Oh my God, these authors are too funny. So apparently Sagittarius A star is part of the name. Sagittarius A star, pronounced like that. The angular size of Sagittarius A star has been measured using radio interferometry. So anyway, they've measured this. They've measured this. Observations by the Chandra X-ray Observatory reveal that Sagittarius A star is an X-ray source as well as a radio source. So now we know it's also X-ray source. We already knew about the radio source. The X-ray emission from Sagittarius A star varies significantly on timescales of less than 1 hour, revealing that the majority of its X-ray emission must come from a region less than one light hour across. Let's review what we know about Sagittarius A star. It is fairly luminous, but highly compact source of radio and X-ray emission located at the galactic center. The bolometric luminosity of Sagittarius A star is not exactly known due to high extinction at many wavelengths, but it is estimated to be around 1,000 solar luminosity. The leading hypothesis is that so this is a hypothesis. Pretty much people believe it. The leading hypothesis is that Sagittarius A star is a supermassive black hole that is accreting gas. A supermassive black hole is a black hole larger than would result from a massive star collapse alone. So this is a supermassive black hole. It's not a normal black hole. I see a new ring on your finger. Did you get engaged? No. This ring, I usually wear it on this hand. I moved it over to the other. I did not get engaged other than to physics. This is my ring to me, from me, by me, for me. Indeed. And yeah, I am married to physics. So this hypothesis, so basically because it's a radio source, it's an X-ray source, it's got some drama with like the X-ray source having a variation. Basically, it's not just a black hole, it's a supermassive black hole, and it's accreting gas, like it's eating up, it's swallowing more things. So that's those other things that's kind of getting accreted by the black hole is what is basically showing up in the form of the radio and the X-ray. The black hole hypothesis is testable by looking at the motion of stars in the vicinity of Sagittarius A star. So how do we know, basically all of this is very dramatic. Plus, we can note the motion of objects around. You need a good man. Do I? Maybe, yeah, could be. So by looking at all the stars that are around Sagittarius A star and seeing how they move, because a black hole is black, even light cannot escape it. If it can be kind of bright though around the black hole, because if it is actively kind of eating stuff, then everything that's getting accreted towards the black hole can actually show up in our observation in terms of the radio and the X-ray like we see here. But yeah, the black hole hypothesis is testable by looking at the motion of stars in the vicinity of Sagittarius A star. If there is a black hole present with mass m black hole much greater than a stellar mass, then stars on elliptical orbits around the black hole will obey Kepler's third law. So, yeah, it's almost like, just like we go around the sun, the stars around the supermassive black hole will kind of go around the black hole and follow Kepler's third law, which gives us something about the semi-major axis of the orbit, of the star's orbit. And P, it's the orbital period. So pretty much we've kind of observed how things move around Sagittarius A star, and also the fact that it's accreting a ton of gas, giving us all these observations. So when it comes to black holes, we do know about black holes. There is observational evidence of black holes. There's more material here on Sagittarius A star. If you're interested, we can get into it tomorrow. They have the the Schwarzschild radius, all that stuff calculated as well. So a lot have been learned about black holes, or quote unquote the dark stars. I would say the bigger mysteries are dark energy and dark matter. We don't know physically what those are yet. But as you can see, as far as black holes are concerned, how they're made, their masses, their size, event horizon, the meaning of that, the Schwarzschild radius, what it's 4 a.m. Gotta go. Awesome channel. Thank you. Okay, have a good night. Good morning. Bye. Basically, as far as black holes go, the fact that it's a stellar remnant, its mass, its size, the physics around it, the physics at its Schwarzschild radius, what makes a black hole, observation of black hole, all of this is quite well known actually in comparison to some other topics especially. So given how black holes are, the environment around a black hole can actually be quite bright and give us a lot of clues as to their existence. And also we can look at other stars and their motions and things around the black hole as well, which should follow Kepler's third law. I'm getting sleepy too, which also gives us a confirmation. So yeah, thank you for joining our live stream today. I thought because we talked about some of the things from Einstein's predictions with general theory of relativity, that we should cover stellar remnants. So that's why I kind of gave you a lightning speed review of stellar remnants today, including black holes. And because people were asking about black holes and are they real, I gave you something about observation of our very own supermassive black hole at the center of our own galaxy, the Milky Way, which is called Sagittarius A star. And the strong radio source itself is called Sagittarius A. Sagittarius A star is the black hole. Okay? Oh my God. So, yeah, hopefully this is helpful. Good night. Wonderful live stream. Thank you. Subscribed. Yay. I'll keep coming back for more. Yes, we will be here tomorrow as well, and Saturday and Sunday. Thank you for joining. We will keep continuing and finishing up Einstein's Cosmos and the other results that came out of Einstein's predictions. But today we covered stellar remnants and black hole observation and the fact that black holes are real. What time? So, you know, I think it'll be around the same time. I'll try to go live a little bit earlier, like maybe like 11 p.m. tomorrow. Also, I might go live in the afternoon. So today I did a live. What's my name? Sagittarius A star. I'm a black hole. What time? Beautiful. I see. Thank you. I don't know if I'm going to do my afternoon live tomorrow. Like today I did my afternoon live. I think tomorrow I have a dinner. I think I'll be back around like 11 p.m. Does that work, Anna? So tomorrow is Friday, and Friday is my original Physics Friday day. And a ton more physics loving people usually come to my Physics Friday day. So I hope that we see a lot of these people tomorrow, and it's a lively discussion. I'm 16. Oh, good God. Well, if I'm 16, maybe don't do anything, because a 16-year-old child should probably not be disturbed. Sounds good. Okay, perfect. I'm tired too now. So I'm like, what am I even reading? Keep up the good work. Thank you, Anna. Thank you so much, Anna. Thank you so much. Thank you for explaining this new book. See you next time. Good night. 11 p.m. Boston time. 11 p.m. Boston time. Yes, you have Friday now too. Yes, it's Friday for me as well now. Good night. Good night, Anna. Good night, Heike. Heike, are you going to sleep now? I know it's morning in Finland, so good morning. I mean, it's morning here, pretty much. Good morning. Good night. Yeah, Anna, get some sleep. You probably have to work or have school. I don't know. Sorry about keeping you up. Friday night, it's really nice because, you know, the next day is Saturday. So some people like stay with us for a long time, and we've had some very intriguing, interesting, lively discussion about physics on the Friday nights. So definitely be here tomorrow for that. Yes, okay, I'm gonna do 11 p.m. tomorrow. I'm gonna wrap up my I've got girls' night tomorrow with a couple of my female colleagues, and so I'll just make sure not to stay out too late, and I can come back and do this. I will go to supermarket. Answer my question. I will go to supermarket to buy groceries, ice cream, and so on. VK Sharma, I have something for you. Go watch all of my videos and then I will answer your question. Go watch all my videos and then put a comment on all of them so that I know that you've watched all my videos. Once you've watched all my videos, put a comment on all of them. Come back to my live tomorrow at 11 p.m. Boston time. And then I will answer your question, VK Sharma. You want answers? Earn it. Pleading doesn't work with me. Queen of Swords. So enjoy my videos, VK Sharma. Please do leave a comment on all of them. I look forward to it very much. And Heike, I will see you. See you, everybody. 11 p.m. tomorrow, Boston time. Tomorrow is going to be a party. Tomorrow is going to be a party. Oh, my phone's about to die. Great. This always happens. Please like, share, and subscribe. Thank you. Oh, and so I just also wanted to say that it's not like I will read this full textbook during the live streams. I know some people probably got a little bit intimidated or bored by this, but that's okay because it's about getting the information out of the book as a reference as needed. And because we were talking a lot about black holes and stellar remnant options, I thought that we should cover it more officially from this book. So I did that. So I will be using this book as a reference. I won't read it, cover to cover like I have been with some of the other books, because those books are more digestible, more accessible. This is more of a textbook with a lot of equations. So it's going to be hard to read it really, but I will be using it as a reference. And because it's such a staple textbook, rest assured that you're getting your information from a good source. The source being this book, the textbook. So hopefully that helps everybody who is interested in these topics. You can also just listen to these live stream videos as they get uploaded as a sort of like an audio, just played in the background if you want. I do hope that some of you will comment on the live video upload once it finishes uploading, because that's how I kind of know that it worked out and everything is good with these lives, because they're pretty long, so it's hard for me to check everything. So please let me know if there's any issues later on with the live uploads. Thank you so much. Thank you, Ismail. Thank you for the emojis. Thank you, VK Sharma. Look forward to your comments on all of my videos and live uploads. So please check my channel and give me some feedback. Looking forward to it. Thank you. Bye. Good night.